First of all, this is a redo of my 2022 presentation. I was, let's see, my wife died that morning, and I didn't cancel out, thinking, oh, I have enough time to do the slides. Well, I didn't. Besides, there's many other things going on. So I would like to, everyone involved to understand that I want this presentation to replace that other one on the record, because I did very poorly there, I'm afraid. I've got a presentation that's got schematics and explanation. There it is. And I will try to, I'll be putting up the schematic, reading the explanation. I'll show it briefly, but the problem is we don't have two screens. And really, in a way, it needs two screens. So for those who view the presentation later, they can move back and forth between screens if it's not on, streaming videotape. So let's move from there. The Pennywhistle 103 dates from 1973. Let's go. In 1973, there were no microprocessors, no personal computers. Time sharing was the way you interacted with a computer on a personal basis. And you were interacting with usually a mainframe computer connected through phone lines and modems to a terminal which was usually a teletype 33. The 35s were so expensive they weren't really used for that. Now at that point, in 1968, there had been a decision known as the Carter phone decision. Carter Phone was a company that made a kind of a modem. It was acoustically coupled. You just put the handset in the cups. And it was sold to oil exploration companies so they could hook up their equipment through the phone line to the computer at the main office. The phone companies said, this will blow up our network if you allow it to be used. Because at that time, you had to rent all your equipment from the phone company. And the 101 modem had been originated in 1958 under the influence of the Stretch computer program, and they can tell you about that downstairs. Huge computer for air defense. They needed communication, so the phone company said, well, we can give you half duplex, one way at a time, communication at 110 baud, which was what teletypes used, or 300 baud. I'm trying to think, maybe they didn't go up to 300. I don't know for sure. And the teletype 33 was produced by the Teletype Corporation, but for the phone company, they would put a 101 modem down inside with the guts of it. And that's what you rented from the phone company. Telexes used pretty much the same thing, but they were a 5-level code, not an 8-level code. Now, Carter Phone went to court and won the right to hook up their acoustically coupled devices to it. But that decision also extended to wire connections. You now had the right to wire connect your own equipment to the phone line through a DAA, direct access arrangement, which is a box that the phone company would rent you and connect at the end of their line. So that was the first move forward into connecting modems that weren't telco modems. Now, they also, the 103 modem was the full duplex version. It was always possible. They just did the half duplex first because that was clearly a little more reliable. But there was a demand for full duplex, so when you hit the key, you could see the character come up on your terminal. I've got a book coming out explaining why, but it started a project in 1972 with a nonprofit that had actually gotten the long-term loan of what amounted to Doug Engelbart's computer that he had used for the mother of all demos in 1968, an SDS 940 time-sharing device. And so I heard about this, I came in and volunteered, and in 1972, when I managed to finish my degree, I had dropped out for 4 years, I came and lived and worked in the same building, maintaining it and trying to get it working, which included modems. We did the, hang on a second. Community memory, let's see. Here we go. This was our first terminal. We had a 4-terminal system to begin with. This was at Leopold's Records in Berkeley, which was owned and run by the student government as a means of driving record prices down. And that's a teletype 33 in the box. The box is lined with urethane foam. You can see a little muffin fan on it because you had to get the heat out. And it's in front of a paper bulletin board. Here's what the user saw, and they could stick their hands through the box and have at it. We would tell people, would you like to use our electronic bulletin board? We're using a computer, and there's nobody in between you and the computer. So we got a nearly universal positive response among mostly students who were coming in. And we developed I'd call it user interface. Now we would call it user interface. We didn't call it then. Which allowed them to use it successfully. I like to say that with this system and its following versions that extended to 1992, we opened the door to cyberspace and found that it was hospitable territory. But we were using these old crummy modems that we got donated to us. It's like a wooden box with a section that hinged up, and you would put the phone in the cups there and close the wooden lid, and it would do all of 110 baud, which was all you needed for a teletype. But we wanted better. We wanted CRT terminals, and we wanted 300 baud. So we worked out what specifications we wanted. Now, of course, 300 baud for the CRT terminals, and we wanted the possibility of direct DAA connection, but mostly acoustic. This originator answer mode isn't exactly right. We wanted, look at the next one, we wanted to be able to record and play back teasers on cassette so they could run while it was unattended and be putting up whatever we had to say about what this wonderful thing is without bothering the mainframe. I think we were a little too sensitive about bothering the mainframe. It turns out that didn't matter. But still, playback from cassette was the important thing. To do that, you have to record tapes using the answer frequencies. You got 2 frequency bands. One going one way, that's originate from the terminal, and the other coming back, that's answer. That's coming from the computer. 1070 and 1270 hertz, kilohertz. No, that's not true. 1070 hertz, or 1270. 2025 or 2225 hertz up here. Record it, you had to obviously record your cassette with that. So it has an originate record mode, but it can't do full originate operation. It can't receive on originate frequency. I said that wrong. Receive on answer frequencies. Okay, so we wanted RS-232 or teletype current loop interface. Okay, now I'm going to talk about the active filter for it. So we had one modem that had been given to us. It was in a little drawn metal case. It was a little more modernistic than the wooden case ones, and I basically gutted that and started designing a modem that would fit in there. Now, what did I know about designing modems? Not much. although I had been assured by my friends with whom I was participating in potluck dinners or lunches, they were dinners, yes, every month, I think, or 2 weeks, I don't know. These were gatherings of people who basically were brought together by People's Computer Company, which was a newspaper. It only published 5 times a year, but it was a tabloid paper, and anybody who was interested in an aspect of personal computing, computer gaming, computers in education, could go in there, talk about what they wanted to do, and they would suggest to you, why don't you write that up as an article, and we'll help you publish it. And I did that. So they had more or less sponsored the Community Computer Center in Menlo Park. It's in a little tiny strip mall. And that was a storefront, I think double wide, where they had originally teletypes with modems. And for 50 cents an hour or something like that, kids, mostly the children of researchers and workers at Stanford Research Institute, Stanford AI, and so forth. Kids could go in and learn how to program BASIC and play games and write games. Bob Albrecht, who ran People's Computer Company, had written some books on learning BASIC and on writing computer games for BASIC. He specialized in bringing children together with computers. So the kids could do that. It was like a little laboratory. And that's where we held the potlucks. And people were telling me, well, you know, essentially, it's a loaded word, you know, essentially, if you don't want me to do the work, you have to do the work. Modems are simple. You have a little oscillator that shifts between 2 frequencies based on the data, and you send that out to the phone, and you get it back, and you have a filter or something, you know, waving your arms. Essentially, all you have to do is this, and you have something that detects the difference between the 2 frequencies. It's easy. No, it isn't easy. However, I had just completed my studies in electrical engineering. And one of the professors I managed to draw was Otto J.M. Smith, peppery little man. And it was an automatic controls course. He had been a member of the team. Oh, that's an interesting little question mark there. I like that. A member of the 1950 team at North American Aviation that had solved the problem of why aircraft were falling out of the sky. The 4-engine planes, the DC-4s and some DC-6s, totally unexpectedly were basically ripping their own wings off in flight. Something was going into oscillation. They had to find out because people were dying as a result. So they worked out a method of analysis called root locus. And that's done on what's called the S-plane, but I'm not going to teach you all about that now. That would take another hour at least. And I'm not sure I would do a good job. They developed a method of stability analysis, and that's how he taught his course, explaining the characteristics of filters and so forth through that graphical method on S-plane. So there's a graphical method of analysis, and it's really neat, I must say, but I can't explain it all here. It's like you start with a pole here, a pole there, and as you increase the feedback gain, the 2 poles move together, and then they join, and then they go away. And there's rules about, you know, asymptotes and things like that. And you have to keep them from going into the right half of the plane because it will oscillate and the wings will fall off. So you have to make sure they go into the left half of the plane. So I designed a circuit. The bridge T circuit is a well-known filter circuit, but it's complex to calculate. Where the hell is that? See, I was going to solve my problem of 2 screens by having one printed, but you can see what happens. Anyway, there's the bridge T filter that I had designed. I'm saying that the classical circuit is called a twin T circuit with two T's in parallel from the as a feedback. So these are all operational amplifiers, very common 741 types. And if you look at the schematic of one of these stages, you've got an inverting amplifier. Here's the input resistor, and these two form the feedback resistor. Now, from a DC standpoint, direct current, the amplification is just the ratio of this resistance, the combination of those two, to that resistance. That sets your baseline amplification. Now, your AC characteristics have to do with the capacitors. And you've got one capacitor here that provides an integration function, and the constant of integration, for those who have paid attention in math class, is set by this resistor and that capacitor. And here's a network that is basically a low-pass filter. And that's the parallel combination of these two resistors and that capacitor sets that number. And so that, if you know how to manipulate them, as I say, the rules are actually very simple. You can set a response that will peak at a certain frequency, but not go to infinity. So you can shift the poles on the plane. Poles are where the responses are. And then they each have a slightly different characteristic. You'll see different values for these capacitors mostly, and for these resistors. It means you can build up a response curve that is a Butterworth filter. There's rules to this, again. Surprisingly simple once you realize what you have to do if you're not using this circuit. So I designed this circuit to produce something like 50 dB worth of peaking at the received frequencies, I think the 2025 and 2025, as I recall. And started building it. So that worked. And then we had the problem of discriminating between the two frequencies. Now, it's easy when you don't have a cassette in the line. There's several ways you can do this, and those old wooden modems would have little inductors and capacitors, and they'd have really precise values to the capacitors, which made them expensive. So the trick with modems is always to find that point where you move between a low frequency and a high, and you've got to try to get it as even as possible in there. Because your manufacturing tolerances are going to put it off. And that's bad enough. Usually a modem would have an adjustment. Or you'd have a resistor, and you'd look in the schematic, and it said SBT, which means select by test. We're not going to tell you what this is. You find out. Whatever works for you, put that in there. Anyway, I wanted to be able to take data from cassette. And I see I've got my frequencies wrong here. This is the answer frequencies, I think. No, I'm not sure. The cassette, however, any magnetic tape, and I had spent 4 years working at Ampex designing stuff, and I'd found out the hard way that really strange things can happen in tape systems. I won't go into the why, because I don't want to take up all my time. And cassettes were not very high-quality tape systems. So they would vary their speed. There'd be an offset, there'd be a range within which they would do what's called wow, which is slowly vary the speed. There was flutter, which is fast version of that. And when we got to personal computers, we would find out that, yeah, they're a problem, because that's the system you could use, you could afford for your personal computer. But it was the devil's own problem getting things to load. So the solution is, as your frequencies varied, they would be separated by a constant amount. You had to find a way to make a reference that would vary along with them. And here's what I used to do it. I used the 565. Hello? Oh, I'm pushing the wrong thing. Phase lock loop. It's a bipolar chip. I think Signetics was the main manufacturer, but others made them. You bring your input in here, you have equal input resistors, and you have a comparator, pardon me, which can be an exclusive OR circuit. You have an oscillator in there that's making a square wave oscillator, and that was determined by this capacitor and this resistor. You would compare the input. Well, first of all, you had to square up the input, so it had a very high gain on the input, so it was slamming between high and low inside. You do a comparison with the exclusive OR, and if your oscillator was right on the nose, it would show you what's called a quadrature square wave. It's at twice the frequency, because an XOR will give you an output, active output, when the two inputs are different, whether they're this way or that. Anyway, the oscillator output, the output of this comparator came out here and went back in there. So it closed the loop right away, so that it was trying to adjust the oscillator frequency so that you would match the input frequency. Now there's a correction voltage that's involved in that. And that's brought out, there I go again, over here. In fact, this is the correction voltage. This is some kind of reference voltage that the chip provides. And you looked at that, and this voltage will be going up when the frequency goes high, and will be down when the frequency goes low. Did everybody get that? Because I looked away here. And now, if the cassette is drifting, that voltage is going to drift too. It's basically a voltage that tells you what frequency you're listening to. So I've got a differential amplifier here. And by the way, the schematic is wrong. These resistors, the combination of this and that, is supposed to equal this, and this resistor is supposed to equal that. So this should be 18 or 20K. The parts list has it right. We did ship the right parts, but the schematic was wrong. So you get, and have here one more of my famous bridge T filters. So you get the filtered output, which is the difference between that and whatever that reference voltage is. All right, so this is going up and down with the data. Now, we have the reference for the Schmidt trigger. We have a capacitor and some resistors. And as you know, the capacitor will charge at a rate determined by the resistance in the capacitor. You have an emitter follower here, which will discharge that capacitor when the output goes low, because the emitter is going to follow the base. And I put a little resistance in here so as not to stress that transistor when it had to discharge the capacitor. It's a 22 microfarad cap. The point of which is that with asynchronous data transmission, between each character it rests. there's a stop bit. And that stop bit is the marking condition, which is equal to 1, or indicated it is the same, equivalent to 1. And your start bit goes from that low position to a high. That starts things happening inside the UART. We'll talk about that later a bit. And an oscillator runs and it samples where the bits are supposed to be. If that data is coming in at the expected rate, but if the cassette is varying, it's going to be moving back and forth. At any rate, well, that sets one limit to if you exceed the timing limits, which is about, it works out to 7%, plus and minus, then all bets are off. Your data goes to crap. But within that, this voltage remains within a range that's appropriate. But the point is, during the space between characters, it always goes to a predictable level, which is the low level. So I'm discharging this capacitor to that level. Then we have data come in here, which moves up from that level, and it is read through the Schmidt trigger, which uses this as a reference. So your reference is based upon the capacitor voltage, and your data isn't. So you'll see this voltage varying as the speed varies, and it's also, during a character, it'll start drifting up. If your data stops, then that will drift up to the 12 volts and shut you off. There'll be some garbage in the meantime. But let's say it worked pretty well, because we had at the Homebrew Club, Dan Sokol, the guy who can be credited with copying the basic tapes. He would ask during the meetings, does it work in Felton? Felton in Santa Cruz County had an ITT phone system, an off-brand phone system, as he told everybody. And you would hear impulse noise and basically other conversations on the line and so forth. So his test was, does it work in Felton? He kept asking this in the weeks when I was telling people that the Pennywhistle was coming. And the day came when he had it, and he came in and he said, it works in Felton. He was surprised. I was immensely gratified, because I don't know what I would have done otherwise. I'd have to move to his place or something to debug it. So anyway, the Schmidt trigger reference point moved enough to keep track with the speed variation of whatever cassette was. And there's an adjustment here, but that's very, that's compensated for by the characteristics of the feedback. You don't really need it. I wasn't bold enough to just put a resistor in there, say SBT, select by test. So we had a little adjustment, but that's really not your threshold adjustment. You don't need a threshold adjustment. So that meant we could sell it as a kit, because the hard thing about modems is the adjustment. So this is the detailed explanation of what I just said, floating reference. And I believe, the line break constraint. When you went to a line break condition, which would be a space condition. See, in telegraphy, the whole circuit is a series circuit, out the wire and back. Telegraph keys have this little switch, a lever that will short the key out. That's where you normally leave it, because all of the additional traffic from the line is going through that key and down the line. And so when you get a line break condition, when the line goes down, that is a failure condition. And in this case, it can happen very easily if your terminal gets turned off or something like that. Why don't I see this here? So if you slow down the data, the baud rate, eventually that space will get so long that the capacitor will charge up past wherever it has to be, and it fails. And so I did some calculations here. Line break, yeah, there it is. Oh, I see. Anyway, no, you're not seeing the whole thing. How can I move that up? All right. I'll read it off the paper. So you got the calculations here. You'll see it on the slide when you can see the slide. And the minimum baud rate is approximately 10 baud. 10 characters, not characters, 10 bits per second. So there's a lot of room in this. Okay. Whoops. This got rotated 90 degrees and stretched out. Okay, well, boy, I sure hope too many others didn't do this. I can't fix this right now, but the point of it is there's the output from the filter gets AC coupled, and we do a carrier detect. There's a circuit that, if you look sideways at this, it's an AC couple coming in here. Putting a diode across the feedback resistor means you have a half-wave rectification. So it can't go up, it can only go down in response to the current coming up here. You've got a little capacitor here that smooths that out a bit. Then you have a big capacitor, that's 1 microfarad. And this will slowly discharge because of this resistor to a point where this op-amp operating as a comparator decides, whoops, it's crossed the threshold, I'm going to go from all down to all up. And that's your carrier detect signal. So let's just move past that. So there's the literary description of the carrier detection, which I've just vocalized, so I'm going to move past that. And here's our data transmission path. Here's your data input. Pin 2 on the connector is RS-232 data. These two pins, 12 and 13, are current loop data. So if you want to use the current loop feature of the teletype, that's where you connect it. You've got 4 diodes that form a bridge. You've got an optical isolator, so you don't care what the voltage is out here, just what the current is. The current will cause the LED inside to illuminate. On the phototransistor, you get up to 1,500 volts isolation. You're safe. And both of these sources of data, one after the other, come into a transistor. This is a Schmidt trigger circuit. For those who will recognize it, you're feeding back here, but not enough to hold it in one condition. So that squares up your signal. And so what comes out of here is the data coming in, shifted from the RS-232 bipolar levels or from the current loop. And there's your literary description of what I just said. Now here's our transmit oscillator. You've got the output transistor of the Schmidt trigger shown over here. And now you have some networks, some voltage dividers that can be switched between high and low, the originator answer frequencies. They are just providing a DC voltage here in accordance with what the data is. So the data will cause that by cutting in these resistors that run in parallel with the potentiometers. I mean, they both have potentiometers. It will cause the voltage at the base here to move between two levels. These diodes are there for temperature compensation. And that includes this. So what this does is, this one, the transistor Q6, causes a current to flow based on that voltage. It's an emitter follower. The emitter resistance is R66 and R67. And notice that those are all 1K resistors. The resistor and the collector, same current will flow through that as flows through the emitter. So that produces a voltage, nominally 1 volt. And it shifts with the data. So as your current gets higher, each voltage becomes greater across these resistors that are in the base emitter section of Q7 and Q6. Now, Q7 and Q6 have their emitters go to an emitter follower resistor. So voltage on the base to emitter, will then result in a current determined by the emitter resistance. Now that's 1K for the pull-up version on Q6, and 1/2, 500 ohms, generated by paralleling two resistors for the pulled-down version, Q7. Now what's the point of this? Well, that's feeding current to a capacitor, C21. So if this transistor is turned off, then this current will cause a linear ramp on the capacitor. It will charge C dV dt, for those who understand. So it will charge up. When this transistor turns on, drawing twice the current that this one is, remember this hasn't changed, it won't change, then it swallows all the current provided by Q6 plus an equal amount. So that gives you a negative going ramp on the capacitor. The 555 timer circuit here has two thresholds, which are basically at 2/3 and 1/3 of the supply voltage due to an internal divider. We're using 12 volts here, so that's 8 volts and 4 volts. So the voltage on this capacitor, when it exceeds the high threshold, there's a latch inside here that says the output should turn off, and pin 7 clamps on. It's an open collector circuit that pulls down, and that will pull down here and turn this diode off. So that it basically turns on this transistor. Remember I said when it turns on and off. Well, the data isn't doing that. But, and you remember, the data varies much more slowly than this does. This produces the 1070 or 1270 hertz, or 22 or 25, if I can remember right. So when that turns this, when this pin 7 goes down, this diode blocks, the pull-down transistor turns on, and causes the ramp to start moving downwards until it reaches the low threshold, 4 volts. when that all reverses, the internal latch changes. And it's pin 3. Where's pin 3? Yeah, that's here. I'm wearing my close-up glasses. So that provides a square wave at the intended frequency, and that intended frequency will change based upon this voltage here, which is dependent upon this network or that network, depending upon whether you're in high or low mode, and depending upon the data. So we're using a simple timer circuit, timer chip, producing a square wave, which is symmetric enough. It's supposed to be hard to generate a square wave from these chips, but that's if you don't do any circuit design. You just copy circuits from the book. But this is one way to do that. And there would be some asymmetry based upon the ratio of these resistors to this resistor. Okay. There's the narrative description, which I will gloss over. Oh, it happened again, huh? Great. It didn't happen this way when I... Wait a minute. Okay, but fortunately these happen when we have simple circuits. Here's the 555 output. Just turn your head sideways. And here, this point is connected to the capacitor. So it's AC coupled through this capacitor, high impedance. We have a bridge T filter there. And all that does is take the linear ramp and kind of add a little sort of exponential characteristic to it. So it's kind of sanding off the point to it. And thus that removes some high frequency components. And this removes more of them. We send that out as the audio, which goes to a speaker. We're actually using 2 speakers, one of which to pick up the audio from the phone, and the other one is to transmit it to the carbon microphone. That's what phones used back then. Now, I did some tests, and based on signal generators, I could get a good response from a minus 50 dBm signal, which is rather low. It's way down there, I'll put it that way. Then when I used it on a phone, I couldn't do that. It turns out that I was limited to 35 dBm. So I wasn't as sensitive as I thought I was going to be. And I bought myself a poster of a train wreck and somebody saying, "Oh, crap," to remind myself that I hadn't quite succeeded here. But that's what it is. That's the specification. Now, it's basically the carbon microphone that provides enough distortion. And so there's the simple description of what I was trying to say. And so that's our audio output. I'm at my last slide now. Hey. Those wooden box modems, they were priced around $350 because this was not a consumer product. This is a product used by computer professionals with big data centers and things like that. However, now, I guess to tell you how we got from 1973 to 1976, aside from waiting 3 years. When the Homebrew Computer Club started, Marty Spergel was an original participant. He called himself the junk man because he had a little business going, M&R Enterprises. The R is Rona, his wife. And they would bag up little boxes, little kits of parts for construction projects that were published in Popular Electronics. So he had a good relationship with Popular Electronics and Les Solomon. So he came to me and said, give me a design to manufacture. I was talking about this conceptual design, Tom Swift terminal. He says, well, give me that design and I'll manufacture it. Well, it's not ready. It actually turned out never to be ready. But I said to him, but you know what you can do? I have this design that's been debugged and it's been operating. We used that modem for about a year on a community memory system. Pardon me here. And one was as good as the other as far as he was concerned. So he went ahead and productized it. I mean, I did the design of the layout of the circuit board. He did the mechanical design. He had people do it. And he found the parts. He found the rubber cups in a warehouse somewhere. And that's what a junk man can do. I wouldn't have had a clue where to get them. He found them. I worked with him to help write the manual. And he put that on the market in 1976. It was on the cover of the July 1976 Popular Electronics. The initial price was $99. He quickly raised that to, this didn't get that change in here, raised it to $139. I changed that at the last minute, but that version didn't get here. And then it went, so that $139, you could get a modem. You had to build the kit. It cost you $225 if he built it. But it was simple enough to build. Plenty of people did. And if it didn't work, you could send it to Marty, and he would have some people debug it. And if he couldn't get it adjusted because it needed an oscilloscope to do the adjustment right, you could send it in and his techs would do it. This is all operated out of a garage in Sunnyvale. I was making $10 a unit as a royalty. I don't remember what the numbers were, but it's several thousand. And I was happy because he wasn't bothering me. Unlike Osborne, that's a different talk. Okay, so the Pennywhistle survived as a product until 1979. Geez, I'm almost out. I guess at this point, I have another presentation on the Kansas City tape standard. Is anybody expecting that? Because otherwise, it's over for questions. So let me see if we got any questions here.
All right. If you have questions, I'll come to you.
We have a hand.
Well, actually, my first question was going to be: how much did any of the work on the Pennywhistle 103 feed into the Kansas City spec? I actually was.
Okay.
I didn't.
I'll talk about that. The Kansas City meeting was organized by Wayne Green in November 1975. I attended along with many other people from different companies. We each had our little product to push. I was pushing the Pennywhistle. MITS had a 103 modem with no adaptive reference. But Don Lancaster had published an article in the first issue of Byte, which was 1975. I can't remember the month here. I've got it in the talk somewhere. And he made an important advancement. He looked at the UART, which requires a receive clock at 16 times the baud rate. And he said, what if we recorded the data on the tape with a carrier that's 16 times the baud rate? So that's 4,800 hertz for 300 baud. which would shift between that and 1/2 that with the data. And so you can recover a clock from that, either by just looking at it if it's 4,800 hertz or doubling it if it's 2,400 hertz. There's simple ways to do that. And if you do that, you now have a synchronous receiver that tracks with whatever the tape speed is. And it really is brilliant. I wrote an article on that in People's Computer Company. I did a participatory design feature. And a guy named Howard Mauch, M-A-U-C-H, whose company was Percom, I believe. He's in Texas, I think, was one of the respondents. So basically, we went through like one cycle of here's an idea, here's my solution, here's what I think of it. He showed up at the Kansas City meeting. So basically, the Pennywhistle design had no real effect on the Kansas City standard, except for my own experience and proclivities and the fact that I had already written about Lancaster's design. We couldn't do Lancaster's implementation on an existing personal computer because they would have the UART circuitry already built in and using a constant clock. And had we been able to implement that, things would have gone a lot better for cassette data, I'll put it that way. So the only effect of the Pennywhistle design on Kansas City design was to incentivize me to push the whole point that you do have to take care of the speed variation of cassettes. So that's the answer to your question. It's like, I would still like to see the Lancaster version with the variable receive clock implemented on the UART. Since I'm so familiar with the SOL design where we didn't make that receive clock variable, I would like to upgrade that someday and see what kind of performance we can get out of it. It's almost irrelevant because nobody's using cassettes anymore. And, the SOL, the CUTS design, I refused to do that channel design. Bob Marsh did it himself, which I have my reasons for that. But he used a phase-locked loop. And if we could have inserted a 4-bit counter in the feedback loop of that and jacked it up by 16 times, we'd have been very close to it. But then we would also have had to made the receive clock switchable between internal and external. But it would have worked. Any more questions? We have one here.
I just have a very simple question. Where did the name come from? I'm guessing it's because the low cost and the audio tones of the modem.
Mm-hmm. And I was born and educated in Philadelphia. So we learned all about Benjamin Franklin and the story of him being shamed by having spent something on a penny whistle rather than something, substantial. Penny saved is a penny earned, all that crap. So have I actually ever encountered a penny whistle? I doubt it. I've heard people play them, but that's about it. So that's where the name came from. I wanted, in amateur radio, a low-power transmitter is often called a peanut whistle. That was my first idea. Oh, it's a very small tone generation thing, so peanut whistle. But not too many of the people involved were hams, and I quickly changed it to penny whistle. That's the answer to that. I hope you can win some bets on that. Have we any more questions? Okay. Well, I'll be here if you want to talk. And I apologize for the sideways schematics. I still don't know how that happened. That's, it goes along with these little question mark bullet points. because everything's equivalent. I mean, I stored these files as PPT, PowerPoint, but I did them as ODP, which is Open Data Presentation. And there's obviously some very slight differences, and we saw them here. All right, thanks for coming.
All right, thank you, Lee.